In this video, we're going to do a quick rotational kinematics problem where we have a wheel turning. So these equations that we use for rotational kinematics are analogous to the equations we use in linear kinematics and projectile motion, except we have omega for our angular speed instead of v for velocity, and we have alpha for our angular acceleration. And we measure our distances and angles typically when we're doing rotational or circular motion instead of using the distance in meters. So in this problem, we have a small pebble that's stuck in the rim of a bicycle wheel. And if the wheel starts out at rest and has an angular speed of 15 RPM after 2.20 seconds, we want to know the angular acceleration and then the angle that the pebble has moved through in this time. So in the first part, we'll call this part A. We want to find the angular acceleration. First, we'll write out what we have here. So we know that the wheel and the pebble start out at rest. So our initial angular speed is 0 radians per second. Typically, this is measured in radians per second in these problems, but sometimes they'll give us the speed in revolutions per minute. So what we'll want to do is convert that to radians per second. And they also give us the time of 2.20 seconds. So our final speed here, final angular speed, is going to be 15. So this is RPM is revolutions per minute. Sometimes I like to write it out this way so we can see how the units cancel out when we're converting it to radians per second. So we'll multiply this by 2 pi. So 2 pi will convert this from revolutions to radians because this is a measurement of radians per revolution. So that's 2 pi radians in one whole circle. One revolution is one whole circle. And we'll divide this by 60 seconds per minute. And this way our minutes are going to cancel out and our revolutions are going to cancel out, and this will give us radians per second. And this is 1.57 radians per second. So now we just have to use one of these equations here and solve for the angular acceleration. So we have the initial and final angular speed, and we have the time. So we'll go ahead and use this first equation here. So omega final equals omega initial plus alpha t. We know that omega initial is 0, so this term is 0. We just have omega final equals alpha t. So solving for alpha, our angular acceleration, we get omega final over t. Or if you rearrange the equation before saying omega initial is 0, you get omega final minus omega initial over the time. So this is going to be 1.57 radians per second divided by 2.2 seconds. And that's going to give us an angular acceleration of 0.714 radians per second squared. So this is our angular acceleration. And in the second part, we just want to find the angle that the pebble moves through. So if we have our wheel here, and our pebble is at one part, we want to find this angle that the pebble moves through. So this angle here. And this is going to be our delta theta. So we'll use this last equation that we have here since we know omega initial, we know the time, we know the angular acceleration. So we'll call this part B. And then we have delta theta equals omega initial t plus 1/2 alpha t squared. Now again, omega initial is 0, so this term is 0. And then we just have that our angle is going to be 1/2 times alpha times t squared. So that's 1/2 times 0.714 radians per second squared times 2.20 seconds squared. And that is going to give us an angle in radians of 1.73 radians. So this is how you would find the angle. So as you can see, these are really similar to the other types of kinematic equations or other types of kinematic problems that we did in projectile motion, with the main difference just being that we're looking at this as an angular distance and speed and acceleration. So hopefully that was helpful, and I'll probably end up putting up some more of these a little bit more complicated rotational kinematics problems. So thanks for watching, and let me know if there are other types of problems you'd like to see.